All right. For the next talk, we have Annika, who will be telling us about faster query times for fully dynamic case sensor with Outliers.
Yeah, thank you for having me. I just want to mention this is joint work with Leyla and Morteza from Eindhoven University and my supervisor, Melanie. Okay, so let me just start by introducing the problem setting that we have. So suppose we have a point set that dynamically changes over time. So that means at every time step, we can either insert a new point or delete an existing point in the point set. But we don't have any movements here, although we could essentially mimic this by first deleting and then inserting another point. And we call the current point set at time t pt, and the objective. So our overall goal is to, in every time step, be able to output a good clustering, and by that I mean specifically the k-center objective. And as k-center is quite sensitive to outliers, we would also allow to exclude a certain number of points to not include into the k-center objective. So let me just show you a little example how that could look like. So we are starting with these 8 points here, and an optimal k-center with two center with two outliers solution could look like this, for example. And now consider that we are inserting a point here. Now the algorithm has to do something about it because it is not covered by any of the clusters, but we also exhausted our number of outliers. So we kind of have to cover another point, and this could be done by maybe shifting this lower cluster to that point here. And next we could maybe delete that point. Should I maybe make this smaller? Is it? Sorry, it's one. But in that case, it turns out that we, okay, now we are in the case that we deleted one of our outliers. And now potentially the algorithm could exclude one of our points and make one of the existing points in the clusters as a new outlier, but it turns out that we cannot decrease our radius here, so nothing changes. Okay, so far nothing really interesting happened here because like our clusters didn't really change. But I want to show you that there can be some drastic changes if we, for example, okay, so first we include another point, okay? And if we, for example, would delete that center here. So because we're assuming that our clusters are centered at existing points, this cluster would now be forced to be centered at one of the other points. But as it turns out, these have a smaller distance from each other. So it makes sense to open the cluster here and make these 2 points outliers. So that means like our clustering could drastically change in the sense that we could move a cluster to a completely different position. Okay, so what are our goals? We want to be able to, in every time step, output a good approximation to the optimal solution for the k-center with the outliers problem. And we want to do this fast. So we want a query time that is independent of z and also good in terms of the number of centers. But the way we defined our queries is that we output the set of all the centers, so we cannot do better than theta of k, obviously. And we also want a reasonable update time, which is also independent of z. And the bad news for that is in general metric spaces, there's a lower bound of omega k, so we cannot do anything about that. So that motivated us to consider a restricted scenario where we consider matrix of bounded doubling dimension. So let me just quickly define what that is. A metric space has bounded doubling dimension down if any ball of radius r in that metric space can be covered by at most 2 to the doubling dimension many balls of half the radius. So the most natural example of such a class are the fixed dimensional Euclidean metrics, where the doubling dimension behaves as you would expect. So as this example of the Euclidean plane shows, that you can cover this orange ball of radius r with 7 balls of half of the radius, so that is doubling dimension log of 7. Okay, so with this I can state our assumptions. We have bound doubling dimension. Also, we want that the distances between 2 points are not too different, which means that we want that the aspect ratio, which is defined as the maximal distance between any 2 points divided by the minimal distance between any 2 points, is bounded by some parameter delta. And we also want that distance computations are possible in constant time. If that is not the case, we will have to just multiply all of our running times by the respective running time that we have there. Okay, so an overview over our results is that we can maintain so we can deterministically maintain some data structure that allows for insertions and deletions, and we also give a deterministic algorithm for performing these solution queries, meaning that we can output the set of centers at any time, and it is guaranteed to give us a 3 plus epsilon approximation, and the uptake time is given here as epsilon to the minus O of dime log n log delta, where epsilon is some error parameter that we give, and dime is the doubling dimension, n is the current number of points, and delta is the spread ratio. And for the query time, we also get an additional factor of k, as I already hinted at, and we replace the log delta by a log delta factor. So if we compare to existing results in that area, we see that there's one result for general metric spaces that achieves a 14 approximation, and there are several others concerning doubling dimension. So as you can see here, the 2 upper results about this have a quadratic dependence on both k and z. And here I want to show you an approach that is linear in k and actually independent of z. Okay, so first I want to give you an overview of what is known already, and I want to highlight some results that we are going to use for our approach. So yeah, in the static setting, there are these old famous algorithms that all of you know. So we can get a 2 approximation for the vanilla case center. And just as recently as in 2016, there appeared also a 2 approximation for the version with outliers. And in the incremental setting, there are results by Samir and Matthew McCutcheon that yield a 2 plus epsilon approximation for case center and a 4 plus epsilon approximation for the outlier case. And last year in the dynamic setting, there appeared a result that is nearly optimal, so it yields a 2 plus epsilon approximation, and the update time is shown to be optimal up to some polylog and delta factors, so there's nothing much more to do about that. And in the case of outliers, as I just mentioned, for the general metrics case, there's this 40 plus epsilon approximation, and last year, like independently of our work, there also appeared this other 3 plus epsilon approximation that I just mentioned on the slide before. Yes.
So is 2 plus epsilon still possible in dynamic?
Yes, like we don't know. Yeah. Okay, so
does the dynamic case subsume the incremental case? But like the 3 plus epsilon, does that include the 4 plus epsilon for the incremental case as well?
Yeah, but this is about doubling dimensions, so that is for general metrics.
Oh, I
Yes.
see.
Yeah, or like the whole table was about general metrics, and then we split this here and show the doubling dimension.
So does the 2 plus epsilon have a bad example for the outlier? Like, can this one also work for the outlier? The 2 plus epsilon without the outlier? The 2 plus epsilon dynamic case entry without the outlier?
Yes.
Is it shown to be bad for the outlier version? Or you just kind of implemented with if there are.
We cannot really use it because I will also talk about that later, but it's not. Yeah, the outliers destroy some properties that we have there. So. Okay. So the first result that we are going to build on is a dynamic 2 plus epsilon approximation for the vanilla K-center. That was also for bounded doubling dimension. It's deterministic and has update inquiry times both independent of K. Now, if you're wondering about that, that is possible because they have different queries where they, instead of outputting the K centers, they just for every point they return this cluster that is assigned to. And the components they use, the ingredients are navigating nets, which is a data structure by Robert and James Lee, which I will explain in a minute, and a parallelization technique that was used in Sami's paper for the incremental case. And the other work that we are using is a greedy static 3 plus epsilon approximation for the case with outliers. Yeah, Samir already told us about that algorithm in his talk. I just briefly summarize. So we first guess the optimal radius, and then we will greedily choose K clusters that are balls of radius R that have the most points in them, and then we increase the radius by a factor of 3 and add this to our solution. And this we do for K times, and if we guessed correctly, then this will yield 3 plus epsilon approximation. Okay, so the plan is using that greedy 3 plus epsilon approximation and deferring the guessing of the radii to this data structure of the navigating nets, similar as in another paper that I just mentioned. And then we will also make use of the parallelization trick to further improve the approximation factor in the end. Okay, so for navigating nets, let me first introduce the notion of R-nets. So an R-net is a subset of the point set that fulfills 2 properties. So first we have the covering property, which means that any point in the point set has to be a distance at most R from one of the points in the net. And we also don't want too many of these points in the net, and we want them to be far apart. So we also have the packing property, which means that any pair of points in our nets is at distance at least R from each other. And then we will have some hierarchy on these R nets given by so first of all, we have to define some set of radii. In our case, it looks roughly like this. And yeah, I want to explain the hierarchy at this little example. So for simplicity, we can just assume beta is 1. So we have the radii set equal to the powers of 2. And okay, so I just want to explain that picture here. So here in the lowest level, we see all the points that we have in our point set. And for the radius 0, we have to include all of them as singletons because they cannot, none of them can cover any other points because we don't have any radius. And if we go to the next level where we have a radius of 1, then because all the points, for all the points, I assume that this distance is like roughly 1, a little bit smaller, we can subsume the points under these representatives. So for example, I could just choose this point to represent these 3 points, these 2 points, and so on. So I get a coarser and coarser representation. So this will be done recursively. So in the next level, I will just compute an RNet on this and so on and so forth. And some nice properties about these navigating nets is, okay, as you see here, I just showed you some of the levels, but actually there can be like any integer of a power of 2. Yeah, it's actually only these levels are interesting, because at the lowest level we have all the points and all the lower levels would be the same. And at some point, if our radius gets large enough, we will only have one point representing all of the other points, and that won't change in any higher level. So these are the relevant levels, and there are actually only log delta, many of them. And we can also show that for any point on the level R, the number, like the points that are directly or indirectly represented by this point are distance at most 2R. So as you can see here, this point would directly represent the points that are inside this orange ball, and these again would represent points that are at distance R half, and these again would represent other points, and so on. And by some simple geometric sum argument, you can see that it's they can be at most of distance to R, which will be very helpful for the analysis later. And yeah, let me just quickly mention that there are some other approaches using similar structures. So first of all, the greedy 3+epsilon approximation, it doesn't use navigating nets, but it uses some modified variant of the R nets. And the result I also mentioned, yeah, actually uses navigating nets. And there's also a hierarchical case center approach for in the polydynamic case that works in the Euclidean space and gives you 16 approximation. And that also maintains something very similar as it maintains a hierarchy of some, yeah, also modified variant of the R nets. And then the other result that is very similar to ours also uses a similar technique called cover trees, which is just as an overview. So the problem with the navigating nets in the case of outliers is that usually it is a good idea to just go to the first level that has at most k-many points, and that can yield a 2+epsilon approximation. But in our case, it is not clear to which level we should go, because there's no level that guarantees us a good approximation. So I want to show that at this little example. So on the one hand, we can upper bound the radius of a K-center with the outliers approximation by the optimal, like the optimal radius of this KZ center problem by the optimal radius of the K center problem. So in the example here, that would be, so we have these 4 little groups, and I want to have a one center with the outliers solution, and the optimal solution would be to just have all these 3 groups in one cluster and exclude the 3 points here. But if I now want to upper bound the radius of that solution by a K-center solution, I would have to include all of the points. So that could be arbitrarily worse than this radius. So the level that contains at most K-centers doesn't give us a good, a good approximation. And on the other hand, also, we can lower bound our radius by the K+C center radius. And again, here we would then pick all of, because we now have 4 centers, so we would pick all of the 4 balls as their own clusters. But this again is very far away from the optimum and also not a feasible solution in our case. So none of these levels really gives us a good approximation to what we want to achieve. So instead, we were thinking of applying this greedy approximation to find the centers. So for that, we have to maintain the neighborhoods. So basically, as in the greedy algorithm, we have to maintain the small neighborhoods of radius roughly r and larger neighborhoods of radius 3r. And yeah, the small neighborhoods we can store in a max heap so that we can efficiently always take the root of the tree to get the heaviest such ball. And yes. Okay, with that, I can show you the algorithm. So it's basically the same idea, like slightly modified idea, same idea than the greedy algorithm. So for k times, we always pick the root of the max heap, which is the closest neighborhood, the close neighborhood with the highest weight of unmarked points. And we add the center of this to our solution, and then we mark all the points in the extended neighborhood. So we don't remove them because we want to be able to still use them as centers, but they won't contribute to the weight of the other balls anymore. And after doing this for k times, we only check if the weight of the remaining points is at most z, and then we know that we have a feasible solution. And yeah, that is only for one level. And overall, we want to find a good level by doing a binary search in some sense, and then also have multiple shifted variants of the radius set to actually find a good radius. So here's a little example. Again, we have k centers and 2 outliers, and an optimal solution could look like this. And we are like on some level, and what our algorithm does first is computing these close neighborhoods, and then we will pick the heaviest one first, which is this one, mark all the points in the extended neighborhood. Then the next point that the next close neighborhood we would choose could be this one. And in the third step, something interesting happens because now we will actually choose one of the marked points as a center because that has 2 unmarked points in its close neighborhood and it's the heaviest one. So it's actually important that we keep the marked points as potential centers. Yes. So, and then, we want to further optimize the parallelization. So first, by binary search, we want to find a level such that at this level, our algorithm outputs something that's successful, and in the next lower level, something that's not. And because we can show that our algorithm is always successful for any radius that is greater or equal to opt, this implies that our R is upper bounded by 2 opt, and it can actually happen that it's very close to it. So together with the greedy 3 approximation, this only leads to a 6 approximation. But if we do this clever shifting of the radii sets, then we can find an R that is upper bounded by 1 plus epsilon times the optimal solution. And this is how we would get the 3 approximation. Okay, so to sum up, we have we can guarantee to get an approximation ratio of 3 plus epsilon, and we get the promised update times and query times. I didn't tell you about it, but that follows from the data structure and the algorithms. And also, we do not have to know the dimension or the aspect ratio in advance. They are only used in the analysis. And also, we can just specify K and Z when we make the queries. So our data structure is not dependent on these 2 parameters. Okay, so in the end, I just want to state some obvious open problems. So the first one is, can we do even better? So is there maybe something better than a 3 approximation here? And then what about general metric spaces? Can we do something better than the 14 approximation, which was working for our previous adversaries? Or even the question, can we even do something about adaptive adversaries there? And then another point that Samir actually told me was that many people are also interested in optimizing the number of center updates. So that depending on the problem, it might be helpful not to change the centers very often. But yeah, in our case, it would actually require to maintain cluster centers, which we are not doing because we are recomputing them in every time step. So I think that would need a wholly new approach. Thank you very much.
Questions? If there is no question, let's thank you, guys.